Alright, let's start this video with some techniques to evaluate these limits. Many techniques for evaluating limits are based on the following important theorem. Basically, the theorem states if two functions agree at all but a single point C, then they have identical limit behavior at that point C. So our replacement theorem, some books call it, let C be a real number, and we have two functions. F of x and g of x are equal. They're identical for all x values except at point C. If the limit of g of x exists as we approach C, then the limit of f of x also exists, and they're exactly the same. Now this might be kind of confusing. When we do a problem or two, and we especially talk about the graph of it, this will make a lot more sense. But in a nutshell, we have two functions that are identical except at one point. And then if the good function has a limit at that point, then the other function is also going to have that exact same limit at that exact same point. To apply the replacement theorem, you can use the result from algebra, which states that for any polynomial function p of c equals 0 only if, or if and only if, x minus c is a factor of p of x. And that might be a little confusing. It's going to get a lot clearer here in example 4. Find the limit of this function. Find the limit as x approaches 2 of this function. X squared minus 4 divided by x minus 2. Well, our limit as we approach 2, let's try first, always try, direct substitution. Direct substitution. So, f of 2. If we plug 2 in for x, we're going to get 2 squared minus 4 divided by 2 minus 2. Uh-oh. 2 squared is 4, minus 4 is 0. 2 minus 2 is 0. Oh no, we got our indeterminate form. 0 divided by 0, indeterminate form. We can't find what that limit is just yet. So we could make a table and start plugging in a bunch of values really close to 2 and see what's going on. Or, if possible, we can use an algebraic technique. When I look at that numerator, I see a difference of squares. X squared minus 4, and because 4 is a perfect square. X squared minus 2 squared. And you can always break a difference of squares up into a sum and a difference. We're going to have one factor is x plus 2, and one factor is x minus 2. And when you look at that, our denominator is one of those same factors. So we played around with this function algebraically. We factored the numerator, and of course we're allowed to cancel. So those are going to cancel out. So here, f of x was equal to this. Well, we simplified this out. We made it look different. I'm going to call this function g of x. Why not? So g of x equals x plus 2. These functions are exactly the same except for one given point, the point 2. Back up to that replacement theorem. Let f of x and g of x be equal. The functions are identical. These functions are exactly the same, but I just made them look a little different. I factored the numerator and canceled a term. F of x and g of x are the same, except at one point. If I plug x's 2 into f of x, the world blows up. If I plug that same 2 into g of x, g of 2 is equal to 2 plus 2, or 4. That is the one point that f of x and g of x differ. I can't plug a 2 into f of x, but I can plug it into g of x. Every other point, they'll get an identical output. So if the limit of g of x exists, which it does here, I plug that 2 right in, and the limit does exist, and that limit is 4. Then the limit of f of x also exists, and they're the same. So the limit of f of x is also equal to 4 because it is for g of x. And let's even think about this. I wish I had the graph of this. Hold on, back that up. Let's think about this graphically. Here's my xy axes. G of x, I can graph g of x. G of x is x plus 2. So we have a y-intercept of 2 and we're a straight line with a slope of 1. It's going to look something like this. If I were to graph f of x, it would look exactly the same, except here at 2 there would be a hole in the graph. So if you plug this into your TI-89, x squared minus 4 divided by x minus 2, you're going to see a line that looks just like this. If you graph the line x plus 2 on the same screen, those lines are going to overlap. The only difference is, if you zoom in enough on f of x, there is a hole in the graph at 2. It's undefined. When we factored, here we factored and canceled this term out. When we factored and canceled, it's like we paved over the hole. This function had a hole in the graph at 2. When we factored and eliminated, we paved over the hole. And now our graph is x plus 2, which is a continuous line with no hole at that point. An example 5, use the dividing out technique. So first, I'm going to try direct sub. Always try direct sub. X approaches negative 3. So I'm going to have negative 3 squared plus negative 3 minus 6 over a denominator of negative 3 plus 3. So negative 3 squared is 9. 9 plus negative 3 would be negative 6. Minus 6 is 0. Divided by negative 3 plus 3 is also 0. And we have indeterminate form. 0 divided by 0 is a bad thing. But we might be able to find this limit as we approach negative 3 by dividing something out. So always look for a clue in your denominator. Here our denominator is x plus 3, or it could be in the numerator. This is probably going to be one of the factors in my numerator, because if it's not, I can't cancel it. So this more than likely will be. These problems are designed to be solvable. So when I look at my numerator, x squared plus x minus 6, I'm going to factor that into two factors. I know the leading terms are both going to be x's. The factors of 6 could be a 1 and a 6, but this is a clue here. One of them's got to be a 3, so the other's got to be a 2. Because this is a plus, more than likely this is going to have to be a plus 2. And if we do our thinking about our foiling out to get a plus 1 in the middle, plus 3, this is going to have to be a minus 2. And we can check by foiling. If we foil that out, we do get our numerator polynomial back, and our denominator is x plus 3. So lo and behold, we will have this cancel out. So this limit, as x approaches negative 3, is also the exact same as the limit as x approaches negative 3 of this function. After we canceled out, we're just left with x minus 2. So if we plug that negative 3 in now, we get negative 3 minus 2, which is negative 5. And because this function, after we factored, is the exact same as the one above, you know, this function, we cannot plug that direct substitution in. We get 0 divided by 0. Here it works. Our limit is negative 5. So the limit of our original function is also the same negative 5. Example 6. Find the limit of a function. Now we're approaching 0. The limit as x approaches 0. Always try direct substitution. We're going to have here, when we plug in 0 for x, 0 plus 1 is 1, the square root of 1 minus 1 in the numerator. And we plug 0 in the denominator. Square root of 1 is 1. 1 minus 1 is 0, divided by 0, indeterminate form. So we cannot evaluate this limit as it stands. We could make a table and go through all that, or we can try another technique. In the previous one, we tried to factor and divide out. Here, we're going to try a rationalizing technique. We want to get rid of the radical. That might be what's causing us trouble. So I'm going to rewrite my function here. Quantity x plus 1 rooted minus 1 divided by x. I want to rationalize. Sometimes it might be the denominator. This time it's the numerator. We have this radical. I want to multiply by something that's going to get rid of that radical, and I'm also going to have to multiply the denominator by the same thing. So we need a conjugate. What is the conjugate of the numerator? Well, the conjugate is going to be the same two terms with a different sign. This here is a minus sign, so my conjugate's going to have a plus sign. The terms are going to be the same. Here I'm going to have a radical, x plus 1, and a 1. And that is going to be exactly the same in the denominator. If I multiply the numerator by this, I got to multiply the denominator by the exact same thing. And now that I look at it, I might almost run out of room, so let me shrink this up a bit. Now we FOIL it out. So this is going to be equal to, and the reason we choose the conjugate is now we have a sum and a difference of two of the exact same things. The terms are the same, the sum and the difference will cause the middle terms when we FOIL this out to disappear. So first term times first term, radical x plus 1 times radical x plus 1. That is radical x plus 1 quantity squared, and the square and the square root will cancel. So what happens is we get the same term without the radical. Radical x plus 1 times itself is just x plus 1 without the radical. If we continue to FOIL, here we're going to have a plus the radical, and here we're going to have a minus the radical, so those middle terms will cancel, and that was the whole point. We wanted to get rid of the radical. Now the middle terms have canceled, and we're left with negative times positive is negative, our last terms. 1 times 1 is 1. So there's our new numerator with being rationalized. We got rid of the radical. X plus 1 minus 1, that is just going to simplify down to an x. Now in the denominator, we didn't have a radical before, but now we have one. And you might want to distribute this x, but let's not for right now. So we're going to have this x times our conjugate. Parenthesis, radical x plus 1, quantity, and then plus 1, close parenthesis. So let's see what happens in the numerator. The plus 1 and the minus 1 are going to cancel. So plus 1 and minus 1 is 0. So now our numerator is just plain old x. And look at that in the denominator. We also have an x. Now, we got to sort of remember there's a placeholder here. There is a 1 here in front of that x. This is a 1x. Because we're going to cancel those x's out. But that doesn't mean the numerator is now gone and this is just the denominator is left. We have a 1 up there holding its place. So when we cancel the x's, we're now left with a numerator of 1 over our conjugate, radical x plus 1 plus 1. So we took this function and we didn't change it. We made it look a little different by multiplying by the conjugate, but this function is still intact in here. So we can look at the same limit as x approaches that 0. So let's try direct substitution now. Plug that 0 in. Our numerator is just a plain old 1. And now down here we're going to have 0 plus 1 under the radical. Well, 0 plus 1 is 1. The square root of 1 plus 1. And the square root of 1 is 1. So we get 1 divided by 1 plus 1 is 2. Our limit as x approaches 0 of our new function is a half. So the limit as we approach 0 of the original function is the same, 1/2. The functions have the same behavior. Now a new topic here, one-sided limits. And this, if we flash back to this example, example 2, when we had the absolute value bars in there. Graphically, I think it's easier to see. As we approached from the left, our limit was -1. As we approached from the right, or numbers greater than our arrow number of 1, our limit was 1. And we saw this in the table. As we approached from the left, our limit was -1. As we approached from the right, our limit was +1. We were approaching two different numbers, so we said overall, that limit does not exist. Remember, we had these rules here. Where is it? Number 2. As we approach from either side, we approach different numbers, so that limit did not exist. But if we want to look at that as a one-sided limit, we have the one-sided limits exist. So back to example 2b, we saw that one way in which a limit can fail to exist is when the function approaches different values from the left of c than it approaches from the right of c. This type of behavior can be described more concisely with the concept of a one-sided limit. So the notation's pretty much the same except for this little superscript number up here, like an exponent. The limit as x approaches c, and there's a little negative up there. That means we're approaching from the negative side of the quadrant, or the negative side of the coordinate plane, or from the left-hand side. The limit as x approaches c from the left of the function f of x is equal to L. And now the other one is the limit as x approaches c from the plus, or the right side of f of x is equal to L. The first of these two limits is read as the limit of f of x as x approaches c from the left is L, and the second, the limit of f of x as x approaches c from the right is equal to L. So find these one-sided limits. Find the limits as x approaches 0 from the left and the limit as x approaches 0 from the right of this function. The function is f of x equal to the absolute value of 2x over x. Okay, so our limit as we're approaching 0. So here is 0. We can't directly substitute that in, or we get our indeterminate form. But if we start plugging in numbers, and again we can use our TI-89 calculators on this. So here at negative 0.1, when we plug that in, we get an output value of negative 2. When we plug in negative 0.01, we get an output value of negative 2. When we plug in negative 0.001, we also get an output of negative 2. And if we come to the other side, numbers above our arrow number of 1, at 0.1, we have an output value of positive 2. And for 0.01, we get a value of positive 2. And 0.001, we also get that same output value of 2. So this is a lot like previous example, but let's write our new limit notation, our left and right-handed limits. So here we're approaching from the negative side, or numbers less than our number of interest 0. So here I'd write the limit as x approaches 0 from the left, from the negative, of our function f of x, and I'm not going to rewrite the function. That limit is equal to negative 2. And then here for numbers above our 0, our number of interest, we would write the limit as x approaches 0 from the plus side of the function f of x is equal to positive 2. And if I were to combine these and just write the limit as x approaches 0 of f of x equals, well, that would be dne. Does not exist. Does not exist. The existence of the overall limit is dependent on the left and right-handed limits. Here the left and right-handed limits approach different numbers, so the overall limit does not exist. But the limit from the left is negative 2. The limit from the right is positive 2. But since those are different, the limit fails to exist. In example 7, note that the function approaches different limits from the left and right. In such cases, does not exist, and we already went over that. For the limit of the function to exist, both one-sided limits must exist and must be equal. So here's our theorem: the existence of a limit. If f is a function and c and L are real numbers, then the limit as we approach c of our function is equal to L if and only if the left and right limits are equal to that number L. In example 8, this is our first experience here with a piecewise function. So our function f of x is broken up into two pieces. We use this piece of the function for minus x for x values less than 1. And we use this piece for x minus x squared for x values greater than 1. And they're asking us here to find the one-sided limits as f of x as x approaches 1. So, and you can see here, this is a dead giveaway, we're approaching 1. 1 is our number of interest. If we were to graph this, to the left of 1, we would have a graph of this. And to the right of 1, we would have this graph. So, and the easy way to do these is, let's just try direct substitution. We're going to plug 1 in to the first piece. So f of x equals 4 minus x. And if we plug in a 1 there, f of 1 equals 4 minus 1. And that's equal to 3. So the limit as x approaches 1 from the left side of f of x is equal to 3. Now let's check the other chunk for numbers greater than 1. So here, our piece of the function is 4x minus x squared. 4x minus x squared. And we plug in a 1. F of 1 is 4 times 1 is 4 minus 1 squared is 1. So here, f of 1 is also equal to 3. So the limit as x approaches 1 from the right side, from the plus side, of our function f of x is also equal to 3. And now we can combine this. Because our left-hand limit is 3 and our right-hand limit is 3, we can write with great confidence the limit as x approaches 1 of f of x is equal to 3. And let's see, no, I didn't put the graph in here, but the graphing is so much fun. We'll just do a quick sketch. I don't want to go into great detail, but here's our function, or here's our xy plane. Our number of interest is x is 1. At 1, we know both functions gave us an output value of 3. So let's look to the left of it, 4 minus x. 4 minus x, if I wanted to graph that, I'd think about it as negative x plus 4. And if I was going to graph the line negative x plus 4, it would have a y-intercept of 4. And I'll switch to red, y-intercept of 4, and a slope of negative 1. So the line would be coming down this way. But remember, that's for x values less than 1. So to the left of 1, we're graphing this line. And now let's see what happens for greater than 1. For greater than 1, we have 4x minus x squared, or negative x squared plus 4x. The squared tells me it's a parabola, and the negative tells me it's downward opening. And if we plug in the 1, we're right back here at 3. So here we're going to have a roughly looking a downward opening parabola. So here's the graph of our piecewise function. And because the limit from the left and the right were equal, you know, that point was shared by both of the graphs. It was a point on this line, it was a point on this parabola. So that is the transition between them, and we are defined at that point. Last topic, I believe it is here, is unbounded behavior. Example 9 shows a limit that fails to exist because the limits from the left and the right differ. Let me do this. Okay, let's think about this one with the table here. We're approaching 2, so in here's our number 2. If we plug 2 directly in, 2 minus 2 is 0, 3 divided by 0, the world blows up. So we're going to see what's happening on either side of it. And again, we can use our TI-89s. So if we plug this into the y-editor and we check the number 1.9, we plug 1.9 in there. 1.9 minus 2 is a small negative number, 0.1. 0.1 divided into 3 gives us negative 30. If we plug in the 1.99, 1.99 minus 2 is negative 0.01, and divide that into 3, and we get a y value of negative 300. And we plug in the 1.999, and we get a small negative number, divide that into 3, we get negative 3,000. If we plugged in the next one, 1.9999, we'd get negative 30,000, then negative 300,000, then negative 3 million. The closer we get to 2, it's like the graph is plummeting off. It's just dropping and dropping and dropping. So it looks like the limit as x approaches 2 from the left-hand side of our function f of x is heading for negative infinity. It's going down, down, down. If we start to plug in numbers to the right of 2, above 2, if we plug in 2.1, 2.1 minus 2 is positive 0.1, divided by 3 is positive 30. If we plug in the 2.01, 2.01 minus 2 is 0.01, divide that into 3, and you get 300. And for 2.001, we get 3,000. If we were to plug in 2.0001, we'd get 30 grand, and then 300,000, then 3 million. It looks like the limit as x approaches 2 from the right side of our function f of x is equal to positive infinity. Now, this might be somewhat misleading, and let me just pop over here to this real quick. This is in your notes. The equal sign, when we say the statement, the limit as x approaches c from the positive side or the right side of f of x is infinity, does not mean that the limit exists. On the contrary, it tells you that the limit fails to exist by denoting what we're going to call unbounded behavior as we approach that number c. I like to think of it like this. Infinity is not a number. Infinity is a concept. Remember, limits are equal to numbers. The limit is equal to some number L. We're using capital L's. A limit is a number. Infinity is not a number. It's a concept. So the limit, as if it's equal to that, well, it's not equal to a number. It's equal to infinity or negative infinity. So these limits really do not exist. And they do not exist because of what we have called unbounded behavior. You know, a limit is a number that we can approach and maybe obtain, but maybe not. Infinity is not a number you can approach. For every number, there's always one out there a little bit bigger. So this is limits fail to exist by unbounded behavior. And that is the end to our introduction to limits.